Hi, this is group number 9's presentation on KSP. My name is Shelby Coelho. I'm going to talk to you about the essential things that you need to know about KSP. It is also known as the solubility product constant. It refers to the equilibrium between a solid and its respective components in a solution. At equilibrium, there is no dissolution or precipitation. Dissolution is when you go from a solid to the components in a liquid. Precipitation is when you go from the different components and you recombine into a solid. This process can take anywhere from seconds to centuries. The value of KSP indicates the degree to which a compound can dissociate in water. A higher KSP value indicates that the compound is more soluble. When writing a reaction for it, we only include the products of the reaction because the reactant concentrations remain essentially unchanged.
And I'm Tereshell, and I'll be showing you a small demonstration of solubility. So here, I'll be putting sugar, regular old sugar, into a cup of water to see how soluble it is. Now, I'll be putting it in, and I'm going to use the stirrer to stir it up. And as we can see, it is dissolving into the water, just like it does when you put it in coffee or tea or anything like that. That's because simple sugars are soluble in water. And now we'll show an unsoluble one. So we have sand here in the same water. And you see all of the particles are moving around and settling at the bottom. There's nothing that's dissociating into the water. This means it's an unsoluble, and it's insoluble in water. Now, there's something else called the limit of solubility. That's where a soluble compound can no longer go up to, it can no longer dissociate completely into the liquid. So we're going to take this soluble sugar and add some more until we reach its solubility limit. So we're adding another one, and we're going to stir it up. And this time, you see there's a chunk down here of particles that are still solid. So that means it's reached its solubility limit, and therefore still has some solids in there.
I'm Sam Dennis, and I'm going to talk to you about how KSP, relates to hazardous waste. So how does KSP affect hazardous waste? It can help classify hazardous waste and tell us a lot about its mobility in water. So let's take a classic Dr. Nelson example. Say we have a tannery, a leather tannery, and the wastewater coming out of the tannery has an excess of chromium. Now, chromium in excess is bad, whether it's in solid or in liquid. But let's say it doesn't dissolve, it's not soluble. Well, if it's not soluble, it will not be able to percolate through the soil with the rest of the water. And it'll still be bad because although it's filtered out, it will still pollute the ground. But let's say it is soluble and it's able to percolate into the groundwater. Well, then you have a lot of toxic material in your groundwater. And that could be a lot worse depending on the situation. And it's also able to tell us something very specific about toxicity in the materials that are soluble in groundwater. There is an identification system is called the soluble threshold limit concentration. And it's the amount of a material, when dissolved or soluble in water, it will become toxic. And there are tables online on how much material would need, how much concentration it would be before things become toxic. And this is a good way of identifying hazardous wastes.
Hi, my name is George Benitez, and I'm going to show you through an example of KSP. So the statement reads, given the chemical equation for the dissociation of silver chromate below, what is the concentration of chromate if the concentration of silver is 0.5 millimoles? If the STL for chromate is 5 milligrams per liter, determine if the solution is toxic. What if the concentration of silver is equal to 0.1 millimoles? Assume STP and 1 liter of solution. So here is our balanced equation. Now writing the equation for KSP, we have KSP is equal to the concentration of silver times the concentration of chromate. Since there are 2 moles of silver per 1 mole of chromate, we have A2, so it's squared. KSP is known for this equation and is equal to 2 times 10 to the negative 12. So now solving for chromate, we have concentration of chromate is equal to 2 times 10 to the negative 12 divided by the concentration of silver squared. And this is known as 5 times 10 to the negative 4. So our concentration is equal to 8 times 10 to the negative 6. Now converting to milligrams per liter to check if it's toxic, we use the molecular weight of chromate as 116 grams per mole. And it's equal to 0.928 milligrams per liter, which is less than 5, so it's not toxic. Now to check if the 0.1 millimoles of silver is toxic, we just redo it, the equation, using the new concentration of silver. So our new concentration of chromate is, let's just solve for milligrams per liter. So for a concentration of silver of 0.1 millimoles, we get 23.2 milligrams per liter of chromate. So that would be toxic because it's greater than 5.
Thanks for watching our presentation.
Bye.